So I put the two graphs up. You can ignore C, just look at A and B. A and B, as soon as I ask the question, which has greater variation, or graph B has greater variation than graph A, or the data in graph B, all of you said true. I didn't hear one person say false, I heard at least half of people say true. So you obviously, something in your gut tells you that the data there is more variable. But the question is why? Who wants to explain why? I'm going to put the screen up, that might be helpful. Say, who's Harrison, go.
Oh crap.
I have a fairly good earring for a punk rock drummer.
Is it because most of the data is like in the first intervals coming out?
Think about what standard deviation is.
Yeah, it's in the...
I do ask you to interpret this on the out-of-class exam. At some point on the out-of-class exam, I say, okay, you just use Excel to calculate the standard deviation of all those numbers. Tell me what that number means. And I give you a hint. I say use the word average twice in your answer. So what is the standard deviation of a data set? Natalie?
The average distance from the average.
It's the average distance a data point is from average.
Now, could that be termed an amount? Like amount of data, then?
Well, the problem with the amount of data is I can't tell how much there is in this data set because there's no scale on this axis, but we can do it relatively. How's that sound? We can do it relatively. Let's say this is 1. That makes this 2. I guess we can't do that, can we? Because that looks like a little bit higher. It doesn't matter. It doesn't matter. Assuming the scales are the same.
Okay.
So the amount of data we'll assume in both data sets is the same, just to keep that variable down. Because that would change it. That actually could change the answer, but assuming both data sets have the same number of data. I saw a hand go up somewhere. I don't want to ignore that hand. Maybe I did. Maybe I'm just seeing things. So back to Natalie's definition. On average, it's how far a data point is from average. Let's think about some of the data points in these data sets, shall we? Let's think about some of the data points. These are clearly dot plots. These are clearly dot plots. Okay? What would you think the average of this data set is? Ballpark it. It's going to be 3. I mean, it's almost a perfect bell shape. It's not perfect. It's a little higher in this bar, and this bar, a little higher in this bar. We're going to call that average. I'll do this. It'll cover our butts. The average is essentially 3, isn't it? If you had to pick a balance point, you'd probably put it right at 3. Okay, what's the average here, friends? This is average of data set A, average of data set B. If you had to pick an average there, what would you pick? I'd pick 3 again. Think about where that would balance. If you had to put, if those are like bottles on a tray, and you had to balance that, chances are you'd put your finger right there. The heavy on this side and the heavy on this side would balance out. I know this is 1 and this is 5, but going with what Robert said, this is a number, and this is a number of data points. So they weigh the same, even though their number values are different. They're weights. Think about what weights are. Weighted averages, the weights are the frequencies. So this bar has essentially the same weight as this bar, because there's just as many of them. Is that fair?
Yes.
Awesome. Okay. Now let's look at the distribution. I want to make some values up. Let's call, can we do this like, 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. I kind of don't want to do that because I'm forcing values. Let's do it in general. Let's do it in general. There are 5 data values in each of these. 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Let's create a little chart here. This is a very long-winded answer to your question, Robert, but I think at the end of the day, it's going to be very, very intuitive for us to put it all together. Because you guys already have the intuition. You knew this was more variable. What we're trying to do is kind of show you why it's more variable. Okay? So here are the data values. Okay. Let's create some distance from the averages for each of those data values. Okay, so far? So for example, 1. How far away from average is 1? It's 2 away, correct? How about 2?
1.
How about 3?
0.
How about 4?
1.
How about 5?
2.
And that's going to be exactly the same down here, isn't it? 2, 0, 1, 0, 1, 2. These are all issues. These are all issues because we're approximating the averages. We can't actually get the raw values without the frequency numbers. Now, how many data points are there for each of those? Now here's what you have to think about. Here's what you have to think about. In this data set, most of the data is at the 3, isn't it?
Yes.
Most of the data is at the 3. There is slightly less here and here. And there's very little here and here. With me so far? By function of that graph, it looks to be, I'd say, well, if it's bell-shaped, we can even slap a number on that, can't we? Within 2 standard deviations, how much of the data is in there? 95%. So in that clump in the middle, you've got roughly 95% of your data-ish. The vast majority is close to average. What's the vast majority? Say that again. Somebody started to say it. I heard the bottom. Oh crap, did I just ruin it? I heard somebody saying the bottom graph. See, I'm hearing and seeing things. It's just a matter of time until I start to see. The bottom graph, where's the majority of the data? Good, far away from average, yes? So, the lion's share, definitely there's a slight majority of 5, but here is most of the data. Most of the data is further away from the average. The very little of the data is actually at average. What if you can see this on the screen? I'll make sure I actually capture in this video. I'm really glad you asked for this question, Robert. Thank you. So very little of the data is actually at average. So, when they ask us which one has a larger standard deviation, since the standard deviation, as Natalie correctly said, is an average distance, aren't the distances in this data set larger than the distances in this data set? Some are the same. They both have distances of 2. They both have distances of 2. But this one has far fewer distances of 2 than this one does. This one has more distances that are larger. So by definition, it has to have a higher average, because the numbers are bigger that you're calculating the average of. And then now you're saying to yourself, Rule, what the hell? We're talking about standard deviation, not average. To which Natalie replies, well, you're eating, I'm sorry. Standard deviation is the
average distance. Average.
It's average distance from average. Standard deviation is just one more average measure. It's an average variation. So since on average we have higher distances here than we did here, it has to have a higher standard deviation. Rob, is that okay? You're not quite buying it yet?
No.
Okay.
Because the distances look the same.
The distances are the same. It's how many of each there are. Okay, here we go. Here we go. Let's make some numbers up. Let's make some numbers up. Let's make it a weighted average. Let's make it weighted by putting the weights in. Because this is, I think what's driving us crazy is we can't put concrete values in. Let's call this 1 right here. I'm already thinking ahead. I'm thinking of this as being 2. We'll call this 2, shall we? That means this 2, I think. Let's put 1 here. 2, 2, 1. Okay. What would 3 be? I guess these would be 3s, yeah?
Yeah.
Could we call that 4?
And the one above it.
And the one above it 4? Okay. 5s? And a 6? How's that? And then they call this one a 6? Okay, you guys ready? This side of the class, right here, calculate 1 bar stats on data set A. 1 bar, this is for an exam review. 1 bar stats on data set A, this side of the class. 1 bar stats on data set B. Okay? 1 bar stats on data set B. While you're doing that, I'm going to pause the camera. I'm going to do a kind of related computation on the